Welcome to the 16th tutorial in the GPSX tutorial series, performing a sensitivity analysis with Python. When first calibrating a model, the sensitivity analysis is a valuable tool to verify the validity of your calibration and view how different parameters impact the model's performance. While a sensitivity analysis performed on a single parameter is valuable to see how it impacts your model, the parameter's impact is often highly dependent upon other parameter settings in the system. By systematically altering various parameters in the system, you can create a sensitivity map to see how various parameters react to one another in the model. The goals of this tutorial are to show users how Python can be used to create a 3D sensitivity map of performance under varied operating conditions. Secondly, we'll see how various plant configurations can be compared within the 2D space using Python to manipulate the scenario being used in GPSX. Please note that the GPSX Pro Plus license is required for Python scripting functionality within GPSX. Additionally, the Python scripts in this tutorial make use of the matplotlib and pillow Python libraries. It is assumed that you have already installed these libraries to the instance of Python you are using within GPSX. If you have not already installed these libraries, please do so before beginning this tutorial. For information on adding libraries to the instance of Python being used within GPSX, refer to the 14th tutorial in the GPSX tutorial series, Using Python in GPSX. Begin by opening the layout created in Tutorial 1 and save it with a new name. Switch to modeling mode if not already selected. Right-click on the influent object and select Composition, Influent Characterization. Click on the Raw button at the bottom of the Influent Advisor to revert the Influent Advisor settings back to their defaults. Right-click on the secondary clarifier and select Input Parameters, Operational. Change the pump flow variable back to its default value of 40 meters cubed per day. Switch to simulation mode. A Python script has been included in the GPSX installation for use in this part of the tutorial. To access it, navigate to the GPSX installation on your machine and select Layouts, Tutorials. Open the script titled Tutorial 16 3D. Save the Python script in the current working directory. Open the Python Script Manager by going to Tools, Python Script Manager. Press the Add button in the Python Script Manager. Select the Tutorial 16 3D script from the file directory and press Open to add the script to the layout. With the script selected, press Edit to open the script in Notepad. The Tutorial 16 3D script visualizes the sensitivity of ammonia in the plant's effluent stream by simultaneously manipulating the plant's operating temperature and wastage flow rate. After performing the sensitivity analysis, Python plots the data to create a 3D sensitivity map which will be saved in the current working directory as a PNG file that is opened at the end of the script. We'll now look at how the Python script is doing this. Notice that the script is broken into 4 distinct sections. The first section is called User Inputs. In this section, the user defines the upper and lower bounds of the temperature and wastage flow rates to be used in the sensitivity analysis. The user can also define the number of equally spaced points they would like the ranges to be broken into. A simulation will be performed using each possible combination of the points. The next section is called Functions. This section contains the start, cint, and EOR functions included in each Python script generated by GPSX, as well as an additional function called GPSX-FN. In the start function, we set the current value of both the temperature and wastage flow rate within GPSX. In the cint function, we are collecting the value of the effluent ammonia at each communication interval. In the GPSX-FN function, we are assigning the current value of the temperature and the wastage flow rate to a Python variable. The third section is the data handling section. This section uses Python's NumPy library to generate a coordinate matrix for both the temperature and wastage flow rates we will be looking at in our sensitivity analysis. Each combination of temperature and wastage rate is then cycled through using for loops, and then the current value of temperature and wastage flow rate is assigned. Using these values, a simulation is then run and the effluent ammonia concentration is collected in the Python results variable. The final section of the Python script is the plotting section. This section uses the matplotlib library to create a 3D axis which the GPSX simulation results are plotted on. The plot is formatted and then saved as a PNG file in the current working directory. Finally, the Python pillow library is used to open the image file and display the sensitivity analysis results. Save the Python script. Press the Run button in the Python script manager to run the sensitivity analysis. After each of the simulations has been run, the output plot will automatically open. From the plot, you can see the nitrification in our process is highly dependent on the amount we are wasting. To further explore how these variables affect our system, try changing the upper and lower bounds as well as the number of points each range is broken into. When deciding on the number of points used in your simulation, it is important to remember that more points will produce a higher resolution plot but will take significantly longer to run depending on the speed of your machine and the complexity of your model. The number of simulations required for the sensitivity analysis does not increase linearly with each additional point. This is an example of a sensitivity analysis conducted with 10 points. This is an example of a sensitivity analysis conducted with 50 points. Next, we will explore how a multivariate sensitivity analysis can be conducted using scenarios in GPSX. Begin by creating a new scenario called high flow derived from the base model. With the high flow scenario active, right-click on the influent object and select Flow Data. Change the influent flow rate to 4,000 meters cubed per day. Right-click on the aeration tank and select Input Parameters, Physical. Set the maximum value to 1,500 meters cubed. Create a new scenario called Low Flow based on the base model. With the low flow scenario active, right-click on the influent object and select Flow Data. Change the influent flow rate to 500 meters cubed per day. Right-click on the aeration tank and select Input Parameters, Physical. Set the maximum volume to 750 meters cubed. A Python script has been included in the GPSX installation for use in this part of the tutorial. To access it, navigate to the GPSX installation on your machine and select Layouts, Tutorials. Open the script titled Tutorial 16 2D. Save the Python script in the current working directory. Open the Python Script Manager by going to Tools, Python Script Manager. Press the Add button in the Python Script Manager. Select the Tutorial 16 2D script from the file directory and press Open to add the script to the layout. Press the Edit button to open the script in Notepad. The Tutorial 16 2D script compares the sensitivity of effluent ammonia in each of the scenarios we have defined as the operating temperature is varied. After the sensitivity analysis is conducted, each of these plants' response is plotted on the same two-dimensional axes, which will be saved as a PNG file in the current working directory. The script is formatted in the same way as the Tutorial 16 3D script with the same 4 distinct sections. We will now walk through what each of these sections is doing. In the user input section, both the temperature range and the number of points we would like to look at in this range are defined. The user can change the value of the wastage rate being used in this section, but unlike the Tutorial 16 3D script, the wastage value is set in the user input section and is held constant across all simulations in the sensitivity analysis. We have also included a target variable that we would like to be met by our model. The functions section of the script contains the same 4 functions as the Tutorial 16 3D script. A new GPSX recognized Python command, GPSX set scenario, is introduced in the GPSX fn function. This function allows you to change the active scenario within the GPSX model by specifying the scenario name as a string within the parentheses. The next major section is the data collection section. In this section, we cycle through each possible temperature value and apply it to each of the scenarios. The effluent ammonia concentration is then collected at the end of each scenario and appended to a separate list for each scenario. Additionally, a list containing the target value is created with a new point appended at each temperature. The value appended is constant for every temperature. The final section is the plotting section. In this section, a single 2-dimensional axis is created using the matplotlib library, and the results of each scenario as well as the target value is plotted on the axes. After formatting the plot and adding a legend, the plot is saved as a PNG file in the Active Directory and opened by the Python pillow library. Save the script. Press the Run Script button in the Python Script Manager to run the sensitivity analysis. After all of the simulations have run, the image will be opened automatically. By looking at the resulting plot, it can be seen that the low flow and base model scenarios have similar levels of effluent ammonia at all operating temperatures, while the high flow scenario always has the highest effluent ammonia concentration. By superimposing a target line, we can see that the low flow and base model scenarios meet the ammonia target at all operating temperatures above about 16 degrees Celsius, while the high flow scenario meets the target above about 19 degrees Celsius. You have now completed the 16th tutorial in the GPSX tutorial series. You should now be familiar with the 2 ways you can perform a multivariate sensitivity analysis within GPSX using Python.